Yesterday you watched an instructional video on Kepler's three laws. The first law, planets move in ellipses with the sun at one focus. It has several implications. The second law, planets move on equal areas and equal times. And the third law is a mathematical equation. This is Kepler's third law, and this is also a form of Kepler's third law. Again, all the planets orbiting a central object, like all the planets orbiting the sun or all the moons orbiting Jupiter, if there are several objects orbiting the same central object, the period of any of those objects over the orbital radius cubed of any of those objects is always equal to some constant k. And as the algebraic theorem goes, if A equals B and B equals C, then A equals C. So any planet, you take the period squared of planet 1 over the orbital radius cubed must equal the period squared over the orbital radius cubed of another planet. This is always true. Both of these are forms of Kepler's third law. What we're going to do, we actually use primarily this equation. See how that is used to understand the motion of planets around the sun specifically. Remember, this can be used for the motion of any object around the central object, like anything orbiting the Earth. The moon orbits the Earth, and satellites orbit the Earth, or Jupiter. Several moons of Jupiter orbit Jupiter, and the same equation holds true for those things. So let's take a look how we can expand those. You have an example problem sheet that you should download to the Notability or print out. These are example problems. You will not be turning this in, but you will have a quiz that's posted on PowerSchool that you will have to do involving Kepler's three laws and specifically using Kepler's third law equation. So let's see how we can use Kepler's third law to do some problems with planets orbiting the sun in this case. So we're going to use Kepler's third law, the planetary motion, to solve these problems. Some information that is given to you is known. This is the orbital radius of the Earth. In other words, this is the distance the Earth is from the sun. This is the period of the Earth, how long it takes the Earth to go around the sun one time. The period is 1 year, or you can call it 365 days, or 12 months, or whatever unit of time you want that at. We'll just say 1 year for right now. Now, let's take a look. Neptune has a period of 164.3 years. What is Neptune's orbital radius? Well, Neptune orbits the sun. So we have to compare it to something else that orbits the sun that we know the information for. Well, that's the Earth. So we're going to put what we know about the Earth. This is the period of the Earth. We know is 1 year. The orbital radius of the Earth is given as 1.50 times 10 to the 11th meters. This is information for the Earth. This is what we know the information for that orbits the sun. Neptune also orbits the sun, so we have information about Neptune. You're given the period of Neptune. It's given in years, so we can write 164.3 years. And we want the orbital radius of Neptune. In other words, how far is Neptune from the sun? Now, important thing to remember, if this is the sun, and this is the Earth, the distance that is given here is always from the center of one object to the center of the other object, not from the surface to the surface, but always from the center to the center. Of course, Neptune is way far out here. Neptune is out here. And so the orbital radius of Neptune is from the center of the sun to, this is Neptune, to the center of Neptune. Always measured from the center of one object to the center of the other object. Right? So let's see how we can do this. We know Kepler's third law, which is this, period squared over r cubed equals period squared over r cubed. So this is the period of the Earth squared over the orbital radius of the Earth cubed is equal to the period of Neptune squared over the orbital radius of Neptune cubed. That's the equation. That's Kepler's third law. But we know all four of these pieces of information except for one. So we're going to solve for that piece of information. We put the values in that we know. Period of the Earth is 1.00 years. We square that. Orbital radius of the Earth is 1.50 times 10 to the 11th meters. We have a lot of numbers in scientific notation on that being. This is cubed equals the period of Neptune, which is 164.3 years, all squared over the orbital radius of Neptune cubed. We're going to solve this. Is now just an algebraic equation. This is the physics that we've done. Now we're going to solve for Rn cubed. We move Rn cubed to the other side of the equation. You should know how to do the algebra for this. It's going to be Rn cubed is going to be equal to 164.3 years all squared. Move this to the other side of the equation. Multiply both sides by this. It's going to be 1.50 times 10 to the 11th meters cubed. We'll get rid of this 1 year, divide everything by 1 year on both sides, 1.00 years, and square that. So now we need to solve this equation. You need to make sure you know how to use your calculator to take the squares of numbers, and we eventually have to get this cube root. Let's see if we can put my calculator and see if we can do this. So I'm going to take 164.3 squared, that's a square symbol, times 1.50, scientific notation, times 10 to the 11th. I'm going to cube that. I'm going to use the caret symbol and push 3, that means cube. I'm going to divide by 1 square. 1 square is 1. We didn't have to do it, but I'm going to do it just to show you the process. We get this value. We 9.11 times 10 to the 37. So this is the orbital radius of Neptune cubed, 9.11 times 10 to the 37. And the units, let's look how the units cancel out. This year square cancels those years square. This is meter cubed, so the units are meter cubed. But we don't want meters, we don't want meters cubed, we want meters. We have to take the cube root of this number. Now, I have a graphing calculator, so that's what I'm going to use in my graphing calculator to take this cube root. You have to know how to use your calculator to take the cube root. In the graphing calculator, I can press math, scroll down to where it says cube root, press enter, and I put this number, and that's the last number I put in. Let's put in the answer, the previous thing that I had in there, or you can type in 9.11E37, and we will get 4.499 times 10 to the 12th. We're going to round that. Orbital radius of Neptune is going to be equal to 4.50 times 10 to the 12th meters. Let me show you another way you can take the cube root of a number if you don't have that math function. I'm going to take this number, this one right here, 9.11 times 10 to the 37, 9.11 times 10 to the 37. I'm going to raise it because the cube root is the same thing as taking something times 0.33333. I'll put 0.33333 as new. I can put a whole bunch of 3's, and we'll get the same thing, 4.98 or 4.50 times 10 to the 12th meters. So you should know how to use your calculator to take the cube root. Okay? Let's do another example. Saturn is 1.43 times 10 to the 12 meters from the Sun. How long is the year on Saturn? So again, Saturn orbits the Sun, so we need to find something else that we know orbits the Sun that we have the period and the orbital radius for. Well, of course, that's the Earth. We know the orbital radius of the Earth, and we know the period of the Earth around the Sun. So again, we have information about the Earth. We know the period of the Earth is equal to 1 year. We know the orbital radius of the Earth is 1.50 times 10 to the 11th meters. And then we have Saturn. We want to know how long the year is in Saturn. That's the period. So the period of Saturn is what we're solving for, and we're given the orbital radius of Saturn of 1.43 times 10 to the 12th meters. We use Kepler's third law. The period of the Earth squared over the orbital radius of the Earth cubed is equal to the period of Saturn squared over the orbital radius of Saturn cubed. We put the numbers in. This again is 1.00 years squared over the orbital radius of the Earth, 1.50 times 10 to the 11th meters cubed. Period of Saturn is what we're solving for. Period of Saturn squared, if we just square that, over the orbital radius of Saturn, which is 1.43 times 10 to the 12th meters, all cubed. To solve for this unknown, again, an unknown has to be in the numerator and by itself. It's like this one up here. This was not in the numerator, so we multiplied it by itself on both sides of the equation so we can get it in the numerator. But the period is in the numerator, so we keep it there. We have to get it by itself. So now we have to get rid of this number. This is in the denominator, so we multiply both sides by that. What we end up getting is 1.43 times 10 to the 12th meters. Don't forget to cube that number times 1.00 years squared over 1.50 times 10 to the 11th meters. All cubed is equal to the period of Saturn squared. So we multiply all this out. Let's see what we get. Show you on my calculator again. I'm going to take 1.43 times 10 to the 12th. Make sure you put a scientific notation. Don't press the time sign and then 12. It doesn't work. Times 10. You put 1.43 EE12. You have to cube that. So put a caret cube times 1 squared. 1 squared is 1, so we don't have to do doing it. And then divided by 1.50 times 10 to the 11th, and then this is cubed. And we get 866.4. And notice what happens. These meter cubed cancel out. We're left with years squared, and that's equal to the period of Saturn squared. Now we don't want the period of Saturn squared, we want the period of Saturn. So we take the square root of both sides. Again, this is the square root function right there. So I'm going to go second square root function. I'll put that answer in there, second answer. And I'm going to get 29.4 years, the period of Saturn. Again, you need to know how to use your calculator to take this square root of a number. You should know how to do that. We've done that type of thing before. Let's do two more example problems. I'm going to do this third one a little bit different. It'll work. Not a whole lot different, but you're going to try and solve it yourself. Let's see how this goes. It takes Mars 1.88 years to travel around the Sun with its Mars orbital radius. So again, it travels around the Sun, so we need to have to compare it to something that we know travels around the Sun, like the Earth. So again, we have information about the Earth. You know, the period of the Earth is 1.00 years. The orbital radius of the Earth is 1.50 times 10 to the 11th meters. And then this is Mars. We're given the period of Mars, which is 1.88 years, and we're going to solve for the orbital radius of Mars. What I would like for you to do now is pause this video and see if you can finish this problem. Do it on your own, and then when you get done, play the video again, and you'll see the solution. So I'm going to solve this solution, but make sure you pause it, see if you can solve this yourself. So, go. All right, hopefully you have this solved. Let's see how it works. Again, we have the period of the Earth squared over the radius of the Earth cubed equals the period of Mars squared over the orbital radius of Mars cubed. Okay. Put these numbers in. This is 1.00 years squared over the orbital radius of the Earth, 1.5 times 10 to the 11th meters cubed. Period of Mars, 1.88 years. Don't forget to square that number. And this is the orbital radius of Mars cubed. Again, we solve this, multiply both sides by the orbital radius of Mars cubed. That comes the left side of the numerator. This is still 1.88 years squared times 1.50 times 10 to the 11th meters cubed. You know, it's kind of a pattern that we get with all these problems so far. And we get that 1.19 times 10 to the, I think that's 34 meters cubed. We get years cancel. Take the cube root of that, we get 2.28 times 10 to the 11th meters. Hopefully you got that. For your answer, when you pause this video and look that through yourself, we do one more. It has a slightly different twist to it. It takes Venus 1.9415 times 10 to the 7 seconds to travel around the Sun. How far is Venus from the Sun in meters? So now, Venus is still something that orbits the Sun, so we still use the Earth. We still have the Earth information. Except notice that this period is in seconds. It's not in years anymore. What I'm going to do, and we still have Venus information, except I'm not going to use seconds. I'm going to convert this to days instead of seconds because that's kind of a cumbersome number to use. So I'm going to take 1.9415 times 10 to the 7 seconds. You should all know how to convert seconds to days, convert seconds to hours, and there's 1 hour over 3,600 seconds. And then convert hours to days. There is 1 day in 24 hours. And we should get 225 days for that. So now I'm going to use the units of days for my period. So we have to have consistent units. We know that the period of the Earth is 1 year. But we're not going to use years, we're going to use days. And we're just going to put 365 days. I know some people, well, why not use 365.25 because this is only one place, to the ones place, so we can use our years to one place. If you want to use 365.25, by all means go for it. It'll all work out pretty much the same. And then, so this is the orbital radius of the Earth in meters, so we can keep that at 1.50 times 10 to the 11th meters. The period of Venus is 225 days, and we want the orbital radius of Venus. We want that in meters, of course. Now again, the reason we did this is to show you that for the period and the orbital radius, the units don't matter, but they must be consistent. If you have one period in days, the other unit must be in days. If you have one period in years, you must have the other in years. Same thing with distances. You can use either meters, kilometers, or miles, or whatever distances you want there, as long as they are consistent, but the process is exactly the same. So again, we have the period of the Earth squared over the orbital radius of the Earth cubed equals the period of Venus squared over the orbital radius of Venus cubed. We put the values in that we know. This is going to be 365 days squared over 1.50 times 10 to the 11th meters. That's all cubed. Period of Venus, 225 days. If we get to square that over the orbital radius of Venus cubed. Now let's rearrange this for the orbital radius of Venus cubed. Again, this multiply both sides by RV cubed. That's going to come over here. And then 225 days squared stays there. Multiply both sides by this, so this comes in the numerator, 1.50 times 10 to the 11th meters cubed. Divide both sides by 365 days squared. We do this calculation. I'll go ahead and do that on my calculator to see what we get. 225 squared times 1.50 EE times 10 to the 11th, raise that to the cube power, divided by 365 squared, and we get 1.28 times 10 to the 33rd, 1.28 times 10 to the 33rd, and the days cancel. It's going to be meters cubed. I take the cube root of that, cube root function, put in my answer. I get 1.08 times 10 to the 11th meters for the orbital radius of Venus. Right. So now, with that, you have had 4 good example problems of how to use Kepler's third law of planetary motion. There is a online quiz that involves information pertaining to all of Kepler's 3 laws and some questions that you have to do calculations for to get the answer using Kepler's third law.